So today we want to talk about RAS, and RAS, as we all know from medical school, is just an abbreviation for Renin Angiotensin Aldosterone system. These are the mechanisms that the brain and the kidney use to help in maintaining homeostasis of the kidney. Usually it helps to maintain the homeostasis of the body. One of the components as to why RAS is usually stimulated is when blood pressure drops. Secondly, when blood volume drops. So when you have low blood pressure and low blood volume, kidney will stimulate the renin angiotensin aldosterone system. And how does the body signal that there is a drop in blood pressure and blood volume? Usually, one, there will be a decrease in GFR, that's a glomerulus filtrate, below the normal range, which is usually 120 to 125 mils per minute. Also, there will be a decreased urine formation, and we will have concentrated urine. So with these two and others that you all know, the kidney will tend to induce the renin angiotensin system to control or to bring back the so-called homeostasis. So as we all know that the kidney is supposed to produce a GFR, glomerulus filtrate, of 120 mils per minute, or that is approximately 180 liters per day of glomerulus filtrate. So now, were it that we urinate all these 180 liters per day, we could run or become dehydrated. So what mechanism usually happens at the nephron, of which we all know the basic function of the nephron? Usually number one is filtration, number two is reabsorption of the glomerulus filtrate, number three is the secretion, just to mention a few. And all these three are the key pillars that helps to produce a GFR of 120 mils per minute instead of 180 liters per day. So this basically means only 1% of GFR forms the urine, while 99% of GFR is reabsorbed in a normal healthy adult. Let's now see what leads to the stimulation of renin angiotensin aldosterone system. So when the body undergoes some sorts of hemorrhagic shock, like severe bleeding post-trauma, two things like anaphylactic shock, which we all know usually leads to vasodilatation, and other factors such as reduced cardiac output. When our body is in such condition, RAS system is stimulated, and the first component that is stimulated is renin. So renin is released from the afferent artery. How is renin released? First of all, in the afferent arteriole, there are so-called juxtaglomerular cells or granular cells. Some people call them renin-releasing cells. So when they detect, or the juxtaglomerular cells detect a decrease in blood pressure in the afferent arterioles, they will stimulate the release of renin. And mind you, the juxtaglomerular cells are baroreceptors. Baroreceptors are cells which are sensitive to blood pressure or pressure. So when there is a decrease in blood pressure, the juxtaglomerular cells, which are located in the afferent arteriole, will release the so-called renin. So the first place place is that renin is released when there is a decrease in blood pressure by the juxtaglomerular cells. And number 2 is that renin is released when there is a decrease in sodium concentration in the distal convoluted tubulus. In what way? Get this clear. So when there's a decrease in sodium concentration, automatically the macula densa cells will be stimulated, and as you know, the proximity, that is the closeness of the distal convoluted tubuli and the afferent arteriole, is just like zero distance. These cells will transmit or signal the juxtaglomerular cells located in the afferent arterioles to release renin. So macula densa cells located in the distal convoluted tubuli detect the decrease in sodium concentration, and therefore, just because they are close to afferent arteriole where the juxtaglomerular cells are located, they will stimulate the juxtaglomerular cells to release renin. So renin will be released. So 2 ways in a nutshell is that when there's a decrease in blood pressure, which is detected by baroreceptors, so-called juxtaglomerular cells in the afferent arteriole, and secondly, when there is a decrease in sodium concentration in the distal convoluted tubuli, detected by macula densa cells located in the distal convoluted tubuli, which in turn, just because they are close to juxtaglomerular cells or the granules in the afferent arterioles, they cause them to release the renin. While the third thing that causes the release of renin from the juxtaglomerular cells in the afferent arterioles is the increase in sympathetic nervous system innervation. When the brain detects a decrease in blood volume and a decrease in blood pressure, the brain will stimulate the sympathetic nerves into the juxtaglomerular cells located in the afferent arterioles to release renin. Remember, renin is just an enzyme, not hormone. Now let's find out on how angiotensin A1 is released and how aldosterone is released. Stick to this video. So once renin is produced from the juxtaglomerular cells of the afferent arteriole of the nephron in the kidney, it will roam around in the bloodstream, and now it will make the liver open the liver to produce a substance known as angiotensinogen, where angio simply means blood vessel and the tensin here refers to the blood pressure, and gen is simply an inactive form. So this enzyme is produced from the liver in inactive form, whereby renin now converts it to angiotensin 1, and angiotensin 1 now moves around in the bloodstream where it goes to the lungs and causes the lungs to produce the ACE, that is the angiotensin converting enzyme. So angiotensin converting enzyme now will convert the roaming around or less clinically important angiotensin 1 to angiotensin 2, which is clinically important. I hope this is very clear, and now let's see what angiotensin 2 does in case we have decreased BP and decreased blood volume. Well, generally, angiotensin 2 now plays a very vital role in blood pressure control and blood volume control. So what it does once it is released into the system after its conversion by angiotensin converting enzyme, it goes to the afferent and efferent arterioles and causes them to vasoconstrict. And when now they vasoconstrict, as you know, is that it causes them to squeeze, to become narrow. And when they become narrow, afferent arteriole will reduce supply of the blood to the kidney, and this will cause the compensation to other vital organs like brain. That is mostly in cases of hemorrhagic shock. And also the efferent arteriole will now decrease blood uptake from the glomerulus capillary, and therefore not much blood will flow to the afferent arteriole to the veins. Number 2, it causes strictly on efferent arteriole the so-called vasoconstriction, and with that, it vasoconstricts the afferent arteriole, making it very narrow, and therefore what happens is that we increase the GFR, that's the glomerular filtrate, and being that we have increased the glomerular filtrate in the Bowman's capsule and the proximal convoluted tubule, automatically we will have also an increase in sodium ion in the distal convoluted tubules. So when sodium ion increases, there is going to be a third enzyme that is now going to produce, and this is none other than the aldosterone system. So the aldosterone system is now going to be produced in what way? The angiotensin 2, and the angiotensin 2 causes the adrenal cortex to release aldosterone hormone, which in turn travels to the proximal convoluted tubule, where initially there is increased sodium ion, and this sodium ion is now going to be reabsorbed back into the bloodstream to help increase blood pressure and blood volume. You know, when there is increase in sodium ion reabsorption back into the bloodstream, the neighboring vessels, that is the afferent arterial and efferent arterial, are going to have high concentration of sodium ion, and with that being said, sodium ion, the vessels of the bloodstream is going to be hypertonic solution, and when we have hypertonic solution next to hypotonic solution, that is next to the nephron tubules, much blood or much fluids will be reabsorbed back into the bloodstream, and that is the feedback mechanism that is going to help increase blood volume and blood pressure. So the other last step or last function of angiotensin 2 is, so angiotensin 2 causes now the brain hypothalamus to stimulate the posterior pituitary gland, the master gland, to release the so-called antidiuretic hormone. Antidiuretic hormone now will travel to DCT, that is the distal convoluted tubule, and it performs two functions. One is that when the body has diuresis or excessive removal of urine or urine incontinence, it will help to stop diuresis. And once we stop diuresis or excessive removal of urine, we will automatically get the feedback mechanism, that is increased blood pressure, and also we will increase blood volume. Number 2 is that the antidiuretic hormone, the ADH, will now help in reabsorption of water back into the bloodstream. In which part? That is none other than the distal convoluted tubule. And once we get the feedback mechanism where we have increased reabsorption of water back into the bloodstream from the nephron tubules, automatically we will have increased blood pressure and increased blood volume. And when we started, we said that RAS, that is the renin angiotensin aldosterone system, is usually stimulated when we have a decrease in blood pressure and a decrease in blood volume. Now you have learned on how we achieve it. Thank you, and stay tuned for the next video.